Alright, so welcome to the sixth video. This problem is going to be about miscellaneous stoichiometry, as it will be covering topics such as moles, masses, volumes, concentrations, and even coefficients of equations. So there's a little bit of everything here. The problem says the following. Hydrated sodium carbonate has the formula Na2CO3 and then a coefficient stated as X, H2O. Now, an experiment was performed to determine the water of crystallization, which is that X. No, a sample of 50 grams of hydrated sodium carbonate was dissolved in 250 centimeters cubed of water. Now, 20 centimeters cubed of this standard solution was reacted completely with 13.95 centimeters cubed of hydrochloric acid with a concentration of 2 moles per decimeters cubed, according to the equation that is given. We're asked to calculate 5 things. First, the amount in moles of hydrochloric acid reacted. Second, the amount in moles of sodium carbonate in the solution. Third, the concentration of that sodium carbonate in the sample. Fourth, the molar mass of hydrated sodium carbonate, so the molar mass of all of this, and then ultimately calculating that value of water of crystallization. Now, parts A, B, and C are relatively straightforward. Parts D and E will require a little bit more thinking and developing. So part A is calculating the amount in moles of hydrochloric acid reacted. We will use one of the most basic formulas in chemistry, which is moles equals concentration times volume. We are given that concentration of hydrochloric acid, and it is given in moles per decimeters cubed, so it is already in standard units, and we can just take that too and plug it into the concentration variable of the equation. Now, we're also given the volume of the hydrochloric acid, but it is given in centimeters cubed. So before we can plug it into the volume variable of the equation, we must divide it by 1,000 to transform it to decimeters cubed. So in the end, we get that moles is equal to 2, that concentration, times the quantity of 13.95 divided by 1,000. We perform all that and we get that the moles of hydrochloric acid reacted are 0.0279. So that would be part A. Part B asks us to calculate the amount in moles of sodium carbonate in the 20 centimeters cubed of the solution used in the reaction. Now, we're asked to calculate something within the solution used in the reaction, so we need to look at the molar ratios of the reactants. We need to see the molar ratios between the acid and the alkali. So in this case, there are 2 moles of the acid, which is hydrochloric acid, that react with 1 mole of the alkali, which is sodium carbonate in this case. So based on this molar ratio and taking this mathematical relationship into account, we're able to determine that the amount of sodium carbonate in the solution that is reacting is equal to the amount of hydrochloric acid divided by 2. Now, we already have that amount of hydrochloric acid from the previous exercise, so we just need to take that amount and divide it by 2, and that will give us the amount in moles of sodium carbonate, as we're taking advantage of the molar ratios of the reactants. In the end, this amount is 0.01395 moles of sodium carbonate in the solution. Now, part C asks us to calculate the concentration of sodium carbonate in the sample. Now, again, we'll be using the essential equation of moles equals concentration times volume. However, we won't be solving for moles, we will be solving for volume. So we take that, we will be solving for concentration, sorry. So we will take the volume to the other side, and we'll get that concentration is equal to amount in moles divided by volume. Now, we're still calculating for sodium, for the characteristics of this sodium carbonate. So we need its amount, and we calculated it in the previous exercise. So we take that amount in moles of sodium carbonate, and we divide it by the volume of the solution. Now, the volume of the solution that is reacting is given to us. It's 20 centimeters cubed, but again, it is in centimeters cubed, and it must be in standardized units, so we must divide it by 1,000 before operating with it. So in the end, we get that the concentration of Na2CO3 in the sample is 0.01395 divided by the quantity of 20 divided by 1000 to get that volume of solution 2 decimeters cubed. If we perform that operation, we get that the concentration of sodium carbonate is 0.6975 moles per decimeters cubed. That will be part C. Now part D is a little bit more extensive, and we need to think a little bit more. So it asks us to calculate the molar mass of the hydrated sodium carbonate. So we're asked to calculate the molar mass of the hydrated sodium carbonate. So in general terms, we know that molar mass is equal to mass divided by amount. Why? Because mass is given in grams, amount is given in moles, and in the end you have the units of grams per mole, which is exactly the units that molar mass is expressed in. So in general terms, the way to solve this exercise is to say, all right, so molar mass of the hydrated sodium carbonate is equal to the mass of the hydrate in the sample divided by the moles of the hydrate. Now we already have the moles of that hydrate. We calculated in part B. We have the moles of the hydrate, which is sodium carbonate, and they are 0.01395. So we already have that quantity, and we could easily just plug it in there. However, for the mass of the hydrate, it is not that straightforward. It is not as if we're given a value that we can just plug into the equation and play with. We need to use some different equations to take into consideration both the water and the mass of the hydrate that is added in order to have a valuable mass of that hydrate within the sample that it was diluted in. So in order to have that mass that takes into consideration all aspects, we're going to first divide the volume of the solution that reacted, which was 20 centimeters cubed, by the total volume of the solution. So that original solution that was made was 250 centimeters cubed, and 20 centimeters cubed were taken out of that 250. So we're going to be taking that volume of solution that was reacted and divided by the total volume of the sample that was initially created. And then we will multiply that times the mass of the hydrate that was added to that water. And that way we will be obtaining a valuable mass of the hydrate within the sample, taking into account all the data that's given and the hydrate itself. Now we have it in centimeters cubed and in centimeters cubed, so this part will not fluctuate the units as they're both in the same unit, and it's not necessary. So in the end, to calculate the molar mass of hydrated sodium carbonate, what we're going to do is 20 divided by the total volume of the original solution, which was 250, times the mass of the hydrate, which is 50 grams. All of that will give us the mass of the hydrate within the sample that was reacted, and we will divide that by the moles of the hydrate in the sample, which we obtained from part B. If we perform all that mathematical operation, we end up getting that the molar mass of hydrated sodium carbonate is 286.74 grams per mole. Now that'll be part D. Now, part E asks us to finally, with all the values that we've been calculating in the previous sections of the exercise, to finally calculate the water of crystallization of hydrated sodium carbonate. So for this, the way to tackle it is to get, because we have already yielded the molar mass of hydrated sodium carbonate. If we manage to have the molar mass of anhydrous sodium carbonate, we can subtract those two and get the molar mass of the water of crystallization, and they take advantage of that number and be able to finally yield that water of crystallization. So since we already have the molar mass of hydrated sodium carbonate, what we're going to do is figure out the molar mass of anhydrous sodium carbonate. So with this, it's pretty easy. We just follow standard procedure to figure out the molar mass of a compound. We take the subscript of sodium, which is 2, and multiply it times its molar mass, which is 22.99. We take the subscript of carbon, which is 1, and we multiply it times its molar mass, which is 12.01. And we take the subscript of oxygen, which is 3, and we multiply it times its molar mass, which is 16. We add those three up, then we get that the molar mass of anhydrous sodium carbonate is 105.99 grams per mole. Now, having this piece of data and having these piece of data allows us to figure out the molar mass of the water of crystallization itself. So we subtract the molar mass of hydrated sodium carbonate, and from the molar mass of hydrated sodium carbonate, we subtract the molar mass of anhydrous sodium carbonate. So in the end, we subtract 105.99 from that 286.74 that we obtained in the previous exercise, and we get that the molar mass of the water of crystallization itself is 180.75 grams per mole. Now, having that piece of data allows us to find the water of crystallization itself. If we divide that molar mass of the water of crystallization by the molar mass of water, we just get the water of crystallization itself. So let's just go ahead and do that. We already have the molar mass of the water of crystallization, and we know, and we can obtain the molar mass of water from the periodic table. So let's just take that molar mass of the water of crystallization. So we have 180.75 and divide that by whatever the molar mass of water is, which is 2 times the molar mass of hydrogen plus 1 times the molar mass of oxygen, which is 16. In the end, the water of crystallization is 180.75 divided by 18.02, which is 10. So in the end, the ultimate goal of the exercise was to get to this, to get to x equaling 10. And I know parts D and E were a little bit more difficult, a little bit longer, and required more skills, but in the end, I hope you learned how to use masses, volumes, moles, and molar masses to your advantage, as well as concentrations, in order to achieve ultimate goals and combine all of those skills and data to get to where you want. And again, the presentation is linked in the description if you find that useful, and thank you.